In physics, heat is energy as it spontaneously passes between a system and its surroundings, other than as work or with the transfer of matter. In thermodynamics, finer detail of the process of transfer is in principle unspecified. When there is a suitable physical pathway, heat transfer occurs from a hotter to a colder body. The transfer can be direct, by contact, from the source to the destination body, as in conduction combined with radiation, or remote, as in radiation without conduction, or indirect, by conduction and radiation through a thick solid wall, or by way of an intermediate fluid body, as in convective circulation. Originally, quantity of heat transferred was measured by how much it changed the states of participating bodies, for example, as amount of ice melted, or change in temperature, without work or matter transfer. Such measurement is possible because many bodies, over most temperature ranges, expand reversibly on being heated. This is called thermal expansion. Historically, when the first and second laws of thermodynamics had been established, it came to be regarded by physicists as more rational to define quantity of heat transferred in terms of equivalent work. Thus, for the sake of logical development, the concept of temperature was reserved for definition in terms of the second law, segregated from the statement of the first law. Kinetic theory explains heat as a macroscopic manifestation of the motions and interactions of microscopic constituents such as molecules and photons. In calorimetry, sensible heat is defined with respect to a specific chosen state variable of the system, such as pressure or volume. Sensible heat transfer causes change of temperature of the system while leaving the chosen state variable unchanged. Heat transfer that occurs with the system at constant temperature and that does change that particular state variable is called latent heat with respect to that variable. For infinitesimal changes, the total incremental heat transfer is then the sum of the latent and sensible heat increments. This is a basic paradigm for thermodynamics, and was important in the historical development of the subject. The quantity of energy transferred as heat is a scalar expressed in an energy unit, such as the joule, with a sign that is customarily positive when a transfer adds to the energy of a system. History. Physicist James Clerk Maxwell, in his 1871 classic theory of heat, was one of many who began to build on the already established idea that heat has something to do with matter in motion. This was the same idea put forth by Benjamin Thompson in 1798, who said he was only following up on the work of many others. One of Maxwell's recommended books was Heat as a Mode of Motion, by John Tyndall. Maxwell outlined 4 stipulations for the definition of heat. It is something which may be transferred from one body to another, according to the second law of thermodynamics. It is a measurable quantity, and so can be treated mathematically. It cannot be treated as a material substance, because it may be transformed into something that is not a material substance, e.g., mechanical work. Heat is one of the forms of energy. From empirically based ideas of heat, and from other empirical observations, the notions of internal energy and of entropy can be derived, so as to lead to the recognition of the first and second laws of thermodynamics. This was the way of the historical pioneers of thermodynamics. Transfers of energy as heat between two bodies. Referring to conduction, Partington writes, if a hot body is brought in conducting contact with a cold body, the temperature of the hot body falls and that of the cold body rises, and it is said that a quantity of heat has passed from the hot body to the cold body. Referring to radiation, Maxwell writes, in radiation, the hotter body loses heat, and the colder body receives heat by means of a process occurring in some intervening medium which does not itself thereby become hot. Maxwell writes that convection as such is not a purely thermal phenomenon. In thermodynamics, convection in general is regarded as transport of internal energy. If, however, the convection is enclosed and circulatory, then it may be regarded as an intermediary that transfers energy as heat between source and destination bodies. because it transfers only energy and not matter from the source to the destination body. Practical operating devices that harness transfers of energy as heat. In accordance with the first law for closed systems, energy transferred solely as heat enters one body and leaves another, changing the internal energies of each. Transfer between bodies of energy as work is a complementary way of changing internal energies, though it is not logically rigorous from the viewpoint of strict physical concepts. A common form of words that expresses this is to say that heat and work are interconvertible. Cyclically operating engines that use only heat and work transfers have two thermal reservoirs, a hot and a cold one. They may be classified by the range of operating temperatures of the working body, relative to those reservoirs. In a heat engine, the working body is at all times colder than the hot reservoir and hotter than the cold reservoir. In a sense, it uses heat transfer to produce work. In a heat pump, the working body, at stages of the cycle, goes both hotter than the hot reservoir, and colder than the cold reservoir. In a sense, it uses work to produce heat transfer. Heat engine in classical thermodynamics, a commonly considered model is the heat engine. It consists of four bodies: the working body, the hot reservoir, the cold reservoir, and the work reservoir. A cyclic process leaves the working body in an unchanged state, and is envisaged as being repeated indefinitely often. Work transfers between the working body and the work reservoir envisaged as reversible, and thus only one work reservoir is needed. But two thermal reservoirs are needed, because transfer of energy as heat is irreversible. A single cycle sees energy taken by the working body from the hot reservoir and sent to the two other reservoirs, the work reservoir and the cold reservoir. The hot reservoir always and only supplies energy, and the cold reservoir always and only receives energy. The second law of thermodynamics requires that no cycle can occur in which no energy is received by the cold reservoir. Heat engines achieve higher efficiency when the difference between initial and final temperature is greater. Heat pump or refrigerator. Another commonly considered model is the heat pump or refrigerator. Again, there are four bodies: the working body, the hot reservoir, the cold reservoir, and the work reservoir. A single cycle starts with the working body colder than the cold reservoir, and then energy is taken in as heat by the working body from the cold reservoir. Then the work reservoir does work on the working body, adding more to its internal energy, making it hotter than the hot reservoir. The hot working body passes heat to the hot reservoir, but still remains hotter than the cold reservoir. Then, by allowing it to expand without doing work on another body and without passing heat to another body, the working body is made colder than the cold reservoir. It can now accept heat transfer from the cold reservoir to start another cycle. The device has transported energy from a colder to a hotter reservoir, but this is not regarded as being by an inanimate agency. Rather, it is regarded as by the harnessing of work. This is because work is supplied from the work reservoir, not just by a simple thermodynamic process, but by a cycle of thermodynamic operations and processes, which may be regarded as directed by an animate or harnessing agency. Accordingly, the cycle is still in accord with the second law of thermodynamics. The efficiency of a heat pump is best when the temperature difference between the hot and cold reservoirs is least. Functionally, such engines are used in two ways: distinguishing a target reservoir and a resource or surrounding reservoir. A heat pump transfers heat to the hot reservoir as the target, from the resource or surrounding reservoir. A refrigerator transfers heat from the cold reservoir as the target, to the resource or surrounding reservoir. The target reservoir may be regarded as leaking. When the target leaks hotness to the surroundings, heat pumping is used. When the target leaks coldness to the surroundings, refrigeration is used. The engines harness work to overcome the leaks. Macroscopic view of quantity of energy transferred as heat. According to Planck, there are three main conceptual approaches to heat. One is the microscopic or kinetic theory approach. Also, there are two macroscopic approaches. One is the approach through the law of conservation of energy taken as prior to thermodynamics, with a mechanical analysis of processes. For example, in the work of Helmholtz. This mechanical view is taken as currently customary in this article. The other macroscopic approach is the thermodynamic one, which admits heat as a primitive concept, which contributes, by scientific induction, to knowledge of the law of conservation of energy. Bailyn also distinguishes the two macroscopic approaches as the mechanical and the thermodynamic. The thermodynamic view was taken by the founders of thermodynamics in the 19th century. It regards quantity of energy transferred as heat as a primitive concept coherent with a primitive concept of temperature, measured primarily by calorimetry. A calorimeter is a body in the surroundings of the system, with its own temperature and internal energy. When it is connected to the system by a path for heat transfer, changes in it measure heat transfer. The mechanical view was pioneered by Helmholtz and developed and used in the 20th century, largely through the influence of Max Born. It regards quantity of heat transferred as heat as a derived concept, defined for closed systems as quantity of heat transferred by mechanisms other than work transfer, the latter being regarded as primitive for thermodynamics, defined by macroscopic mechanics. According to Born, the transfer of internal energy between open systems that accompanies transfer of matter cannot be reduced to mechanics. It follows that there is no well-founded definition of quantities of energy transferred as heat or as work associated with transfer of matter. Nevertheless, for the thermodynamical description of non-equilibrium processes, it is desired to consider the effect of a temperature gradient established by the surroundings across the system of interest when there is no physical barrier or wall between system and surroundings. That is to say, when they are open with respect to one another. The impossibility of the mechanical definition in terms of work for this circumstance does not alter the physical fact that a temperature gradient causes a diffusive flux of internal energy, a process that, in the thermodynamic view, might be proposed as a candidate concept for transfer of energy as heat. In this circumstance, it may be expected that there may also be active other drivers of diffusive flux of internal energy, such as gradient of chemical potential which drives transfer of matter, and gradient of electric potential which drives electric current and iontophoresis. Such effects usually interact with diffusive flux of internal energy driven by temperature gradient, and such interactions are known as cross effects. If cross-effects that result in diffusive transfer of internal energy were also labeled as heat transfers, they would sometimes violate the rule that pure heat transfer occurs only down a temperature gradient, never up one. They would also contradict the principle that all heat transfer is of one and the same kind, a principle founded on the idea of heat conduction between closed systems. One might try to think narrowly of heat flux driven purely by temperature gradient as a conceptual component of diffusive internal energy flux. In the thermodynamic view, the concept resting specifically on careful calculations based on detailed knowledge of the processes and being indirectly assessed. In these circumstances, if perchance it happens that no transfer of matter is actualized, and there are no cross effects, then the thermodynamic concept and the mechanical concept coincide, as if one were dealing with closed systems. But when there is transfer of matter, the exact laws by which temperature gradient drives diffusive flux of internal energy, rather than being exactly knowable, mostly need to be assumed, and in many cases are practically unverifiable. Consequently, when there is transfer of matter, the calculation of the pure heat flux component of the diffusive flux of internal energy rests on practically unverifiable assumptions. This is a reason to think of heat as a specialized concept that relates primarily and precisely to closed systems, and applicable only in a very restricted way to open systems. In many writings in this context, the The term heat flux is used when what is meant is therefore more accurately called diffusive flux of internal energy. Such usage of the term heat flux is a residue of older and now obsolete language usage that allowed that a body may have a heat content. Microscopic view of heat. In the kinetic theory, heat is explained in terms of the microscopic motions and interactions of constituent particles, such as electrons, atoms, and molecules. Heat transfer arises from temperature gradients or differences, through the diffuse exchange of microscopic kinetic and potential particle energy, by particle collisions and other interactions. An early and vague expression of this was made by Francis Bacon. Precise and detailed versions of it were developed in the 19th century. In statistical mechanics, for a closed system, heat is the energy transfer associated with the disordered, microscopic action on the system, associated with jumps in occupation numbers of the energy levels of the system, without change in the values of the energy levels themselves. It is possible for macroscopic thermodynamic work to alter the occupation numbers without change in the values of the system energy levels themselves. But what distinguishes transfer as heat is that the transfer is entirely due to disordered, microscopic action, including radiative transfer. A mathematical definition can be formulated for small increments of quasi-static adiabatic work in terms of the statistical distribution of an ensemble of microstates. Notation and units. As a form of energy, heat has the unit joule in the international system of units. However, in many applied fields in engineering, the British thermal unit and the calorie are often used. The standard unit for the rate of heat transferred is the watt, defined as joules per second. The total amount of energy transferred as heat is conventionally written as Q for algebraic purposes. Heat released by a system into its surroundings is by convention a negative quantity. When a system absorbs heat from its surroundings, it is positive. Heat transfer rate, or heat flow per unit time, is denoted by. This should not be confused with a time derivative of a function of state, since heat is not a function of state. Heat flux is defined as rate of heat transfer per unit cross-sectional area, resulting in the unit watts per square meter. Estimation of quantity of heat. Quantity of heat transferred can be measured by calorimetry, or determined through calculations based on other quantities. Calorimetry is the empirical basis of the idea of quantity of heat transferred in a process. The transferred heat is measured by changes in a body of known properties, for example, temperature rise, change in volume or length, or phase change, such as melting of ice. A calculation of quantity of heat transferred can rely on a hypothetical quantity of energy transferred as adiabatic work and on the first law of thermodynamics. Such calculation is the primary approach of many theoretical studies of quantity of heat transferred.